Hey guys, today we're going to be applying the concept of energy in chemical reactions, but in the form of stoichiometry. So in the last video, we talked about how we could analyze a potential energy diagram to determine if a reaction is endothermic or exothermic. And today, we're going to integrate this into an actual chemical reaction equation and be able to determine quantitatively how much energy would be absorbed into or released from any one reaction given other stoichiometric circumstances. So just as a quick recap and review from last video, remember a positive delta H, a positive change in enthalpy, means that our products have greater potential energy than our reactants, and that means that energy had to be added in over the course of the reaction. That would be an endothermic reaction. That endothermic reaction would be a positive delta H. Exothermic, on the other hand, the potential energy of the reactants is greater than the potential energy of the products. Therefore, energy was released out of the reaction as over the course of the reaction, and the delta H value, the change in enthalpy, would be a negative value. So here's an example of a positive delta H and then a negative delta H. So when doing stoichiometry, remember that we need to always go back to these ideas of equivalencies. Equivalencies could be something like Avogadro's number, where there's 6.02 times 10 to the 23rd particles per mole, or molar mass, where there's a certain number of grams in every mole. Or in terms of the reactions, once we balance reactions, the equivalencies, remember, are based on the coefficients within. So for instance, in a reaction, if something has a coefficient of 2 and the other thing has a coefficient of 3, that means the ratio, the equivalency between them, would be 2 to 3. So in each of these circumstances, we're going to apply unit conversions and mole ratios to be able to convert from one thing to another. That's going to apply in this unit heavily. So let's go ahead and do our first practice problem. Now in this problem, I've got nitrogen in its molecular form reacting with oxygen in its molecular form to produce 2 NO molecules. The delta H of this reaction is positive 180 kilojoules. Now what that tells you as a positive delta H is that we are an endothermic reaction. What I need to do is solve for the amount of energy absorbed when I react a certain number of grams of nitrogen with XX oxygen. So I know that we are going to be able to do this, but let's talk about how. Energy is being absorbed. Well, that means it's going in. Going in. Well, that's like a reactant. So what I'm going to do is I'm actually going to rewrite the equation such that I incorporate the energy into the reaction itself. All right, we'll talk about why that is here in a minute. So what I've done is I've integrated the energy into the reaction. Again, it's an endothermic reaction, which means energy goes in as a reactant. So it's 180 kilojoules on my reactant side, plus a nitrogen and an oxygen to yield 2 NOs. So just like our coefficients could be used in stoichiometry to create an equivalency, we can also create an equivalency with energy. So for every 180 kilojoules, there's 1 mole of N2. And for every 180, there's 1 mole of O2. And for every 180, there's 2 moles of NO. That's an equivalency. So what I'm going to do is I'm going to take the given value, 8.32 grams, and I'm going to use dimensional analysis in stoichiometry to find my answer in kilojoules. So I need to make sure I cancel units correctly. So let's go ahead and do this real quick, starting with what I'm given. Need to cancel grams of nitrogen. Need to get into moles of nitrogen. Remember, in stoichiometry, we're almost always going into moles. All right, moles is the key connector between any chemical reaction. So now we need to get into moles. Nitrogen N2 weighs 28 grams per mole. And now is where I need to convert into energy. Remember, for every 1 mole of N2, there's 180 kilojoules. So there's my equivalency. So now, grams of nitrogen cancels, moles of nitrogen cancels, my final unit's in kilojoules. If I solve for this, it ends up being a total of 53 kilojoules of energy. So to answer my question explicitly, that means 53 kilojoules of energy is absorbed when 8.32 grams of nitrogen reacts with excess oxygen. Let's take our stoich one step further. Now in the last problem, we were reacting with excess of one of our reactants, but in this case, I'm giving you the amounts of two different reactants. That should set off alarm bells. That means we're dealing with probably a limiting reactant problem. We need to address it as so. In this case, we've got hydrogen reacting with oxygen, and it's going to produce water. And I'm given the delta H of the reaction is negative 571.6 kilojoules. I need to figure out how much energy is going to be released when I combine these amounts of each of our reactants. First thing I need to do, figure out who's the limiting reactant. Remember, my technique for figuring out the limiting reactant is to figure out which one produces less of a product. Well, in this case, energy is a product. It's an exothermic reaction. That means if I were to rewrite this equation with the energy involved, I'm going to rewrite it like this. Now, one thing to be careful of. Yes, this is a negative over here, but we don't include it in the reaction equation as a negative. The reason we don't do that is because it's it's a magnitude of energy released. It's a positive amount of energy released. This negative sign here just tells me what was it before compared to what is it after. This, when you incorporate it into the equation itself, becomes a positive value, just as a heads up, okay? Now, that means we have a ratio between moles and energy. So what we're going to do is we're going to use dimensional analysis and stoichiometric skills to be able to get from our grams of hydrogen and our grams of oxygen to our amount of energy produced by each. So, for hydrogen, we've got 14 grams of hydrogen, 2 grams of hydrogen for every 1 mole of hydrogen, and based on our ratios here, 2 moles of hydrogen for every 571.6 kilojoules of energy released. So, we multiply across the top, we divide across the bottom, and we end up, if we were to react our hydrogen fully, releasing a total of 1,985 kilojoules of energy. Now, be careful. I've added the negative back in. Why? Because as I said, it's releasing that amount of energy. The negative sign in a delta H value is just going to tell us the direction. Is it going in? Is it coming out? If it's negative, we're talking exothermic. It's exiting the reaction. It's going out of the reaction. So it's a negative 1985 kilojoules. So we're going to do the same thing with our oxygen now. We started with 92 grams of oxygen. Let's see how much energy it would have produced if it reacted fully. So we've got 92 grams of oxygen, 32 grams of oxygen for every 1 mole, 571.6 kilojoules of energy for every 1 mole of oxygen, again going back to my stoichiometric ratio here, and I end up with a value of negative 1,643 kilojoules of energy released. Well, so what does this tell us? Well, just like it told us when we were looking at limiting reactant in prior units, this value released by oxygen tells me that because it's less than the amount that would have been released by the hydrogen, the oxygen is in fact our limiting reactant. And as our limiting reactant, it limits not just the amount of products produced, but also the amount of energy released, because at that point, the reaction will cease, which tells me that in the end, oxygen is the limiting reactant, and a total of 1,643 kilojoules of energy would be released from the reaction. Again, the negative sign just tells me direction. So if you say 1,643 kilojoules of energy released, you don't need the negative sign. If you say how much energy is released and you don't give it any context, so you just say energy equals negative 1,643. Then you need the negative sign to bring the context of the direction of energy. So that wraps up today's video. Let's do a quick recap. Today we learned how to apply stoichiometric techniques to energy of reactions using delta H, change in enthalpy. All right, so remember, we need to always get into our mole ratios. Always in stoichiometry, the mole is the connecting factor between a chemical reaction and any other aspect of stoichiometry. So I'd like to thank Nick Horsfall and Sarah Bernardo for writing, filming, and editing this video. I'd like to thank you guys for watching it, and I'll see you in the next one.